Okay, so this is your 3.4 foldable, and we're going over 3 new theorems today. All right, so the linear pair perpendicular theorem says, if you have two lines that intersect and they form a linear pair of congruent angles, they have to be congruent, then the lines are perpendicular. So basically, if you look at the picture, we have two lines that intersect. And angle 1 and angle 2 are a linear pair, and you can see the markings. They show that they are congruent. So if angle 1 is congruent to angle 2, then that's enough to conclude that line G is perpendicular to line H. And this symbol right here means perpendicular. All right, so let's look at the next one. Perpendicular transversal theorem. So in a plane, so in one plane, they can't be skew lines. If a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other. So what you have to have two parallel lines. So you see we have here H is parallel to K. The transversal has to be perpendicular or at a right angle to one of those two lines, either H or K. So J is perpendicular to H. So if you have two parallel lines and the transversal is perpendicular to one of them, then you can conclude that the transversal is perpendicular to the other one. So it's saying then you can conclude that J is perpendicular to K. So you can assume that this is a right angle over here. Okay, and then this one to me is the most common of the three. Lines perpendicular to a transversal theorem. So in a plane, if two lines are perpendicular to the same line, so you guys see here line M is perpendicular to P and N is perpendicular to P. So notice they're both perpendicular to the same line, which is P. So if that's the case, if they're both perpendicular to P, then they are parallel to each other. So you can conclude that M is parallel to N based on the lines perpendicular to a transversal theorem. Now, thank goodness for foldables, because memorizing these things, I think they're very easy to get twisted in your head because they kind of sound the same. So I refer back to this foldable repeatedly. Okay, let's go inside the foldable and kind of practice this. So example 1 says, determine which lines, if any, must be parallel. So I like to use a highlighter here. So for example, N is perpendicular to L. So I'm going to highlight the two. Those two are perpendicular to each other, the two lines I highlighted in yellow. All right, let's highlight what else we see going on here. So P is perpendicular to M. Okay, so notice that when I highlighted for my two perpendicular, none of the lines were the same. I highlighted the two lines in yellow and the two lines in green, and I never needed to highlight one line with two colors. So I don't have a linear pair that has two congruent angles. I don't have two perpendicular, two lines that are perpendicular to the same line. And I don't have two lines that are parallel that I already know. So I have nothing here. So literally, are any lines parallel? No, none. All right, let's try another. It gets easier as we go. So example 2. So if you look at what we have here, E is perpendicular to G. So I'm going to highlight E and G here. All right. Okay, so if I highlight E and G, those are those two. Now, also, E is perpendicular to H. So let's highlight E and H. Okay, it's not showing up great, but I'm highlighting E right here, kind of going up and down. Okay, so if you notice, I had to highlight line E. I highlighted it twice. So that tells me, sorry, I can't spell here. It tells me that there must be something going on here. So if you look at it, based on what I've highlighted, I never highlighted line F. So there is nothing going on with line F. So I highlighted that E is perpendicular to G and E is perpendicular to H. So therefore, G and H must be parallel. So I'm going to say G is parallel to H. So my reason why is if E is perpendicular to G and E is perpendicular to H, they're both perpendicular to the same line, therefore they're parallel to each other. So that is, if we go back up here and look, two lines that are perpendicular to the same line, so therefore they're parallel to each other. That is this lines perpendicular to a transversal theorem. So our reasoning when we explain, I'm going to say lines perpendicular to a transversal theorem. Okay, let's look at example 3. All right, so once again, I like to highlight here. I just think that it works better. You could also use just a marker. It doesn't have to be a highlighter. So right here I have line B is perpendicular to A. Okay, so I'm kind of using my marker here because it works a little better sometimes. So then also C is perpendicular to A. So based on this, I didn't ever need D. So D has nothing to do with this at all in any way, shape, or form. So since B is perpendicular to A and C is perpendicular to A, if they're both perpendicular to the same line, then they have to be parallel to each other. So B must be parallel to C. And once again, that's using the lines perpendicular to a transversal theorem. All right, let's look at proofs. I think we're going to use more of these on proofs. Okay, so let's look at what we've got here. So first of all, we have our givens. So just looking at this, angle 1 is congruent to angle 2. That's given. All right, and then we also know F is perpendicular to H. You can see that with the little right angle symbol right here. And F is parallel to G. You can see it with the little arrows that they have right here. These little arrows mean they're parallel. All right, so those are our givens. So now it wants to know, it's like, hey, E is perpendicular to H. Why can we say that? Well, if you look right here, here's E and here's H. And the reason we know that is because angle 1 is congruent to angle 2. So if you look back at the front page of our foldable here, this linear pair perpendicular theorem clearly shows where we've got two angles that are congruent and therefore they are perpendicular. So that's going to be our reason on that one. So why is E perpendicular to H is because of the linear pair perpendicular theorem. Okay, so now we can draw in a right angle here because now we know that E is perpendicular to H. We just stated that on line 4. All right, so now let's take a look at line 5. It says E is parallel to F. So that's this one right here. Here's E and here's F. Now the reason that they're parallel, picture this. Here's E and here's F, and you know these are right angles. And so if they're both a right angle to line H, go back to the front of your foldables, so look for the picture that kind of resembles that. So that to me is lines perpendicular to transversal theorem, which says if two lines are perpendicular to the same line, then the original two lines are parallel. Let's just prove things are parallel. So that was lines perpendicular to a transversal theorem. Okay, so now the reason E is parallel to G, the reason is if you already knew F was parallel to G, that was line 3, and in line 5 you knew E was parallel to F. Well, if E is parallel to F and F is parallel to G, then E is parallel to G, and that's because of the transitive property of parallel lines. Okay, one more proof here. Just some more practice. So let's look at our givens. Our givens are angle 1 is congruent to angle 2. Okay, and then we also know that B is perpendicular to D. We have that marked right there. And then we know that C is parallel to D because of those arrows. Okay, so first of all, when we see that 1 is congruent to 2, so angle 1 is congruent to 2. When we see that, remember that that looks extremely similar to the linear pair perpendicular theorem. And so the linear pair perpendicular theorem is what they wrote on line 4. And what it lets us do is it lets us say if two angles are a linear pair that are congruent, then the lines are perpendicular. So A and C make a right angle right here. So A is perpendicular to C. That's what it lets us say. Okay, so line 5 says perpendicular transversal theorem. So remember what it says. Perpendicular transversal theorem says if you have two lines that are parallel, let's pretend those are parallel, and the transversal is perpendicular to one of them, then you can then prove, next step is you can prove that, hey, this is perpendicular. All right, so if you look at this, we have C is parallel to D. So right here, C is parallel to D. D is perpendicular to B, therefore C must be perpendicular to B. So C must be perpendicular to B, or if you want to say B is perpendicular to C, it doesn't matter the order. C perpendicular to B or backwards, B perpendicular to C. Okay, so now remember, you knew this was a right angle right here because of step 4, and this is a right angle due to step 5. So we want to prove that A is parallel to B. Well, so picture this, you have two lines that are perpendicular to the same transversal. So if we go back and if we look for something that has that kind of a picture, let's go back to the front of the front of our foldable. So that looks very much like this one right here, lines perpendicular to transversal theorem. It said if two lines are perpendicular to the same line, then they are parallel to each other. So they are both perpendicular to line C, therefore they are parallel to each other, and that was the lines perpendicular to a transversal theorem.